How's it going, everyone? Welcome. Oliver Gonzalez here. And today let's going to now look at the number primitive and why this is important, and especially to recap about how do we get here in this particular course, which is deep dive in JavaScript. So the TLDR of this is that Kyle Simpson, which is a software engineer that makes several books, one of them is the You Don't Know GS, and now he described these three pillars that is in JavaScript. Only the language, the specifications, which is the type system, the scope system, right? Scope system, and the object systems. So this is now what the JavaScript is capable of, this pillar. And also now how ECMAScript can be poured or can be run on top of an environment known as the host environment, whether it's a browser or the server. And because of that, now JavaScript can do things like asynchronicity and how it handles that. So by first looking at the callbacks and then the concept like thunk, which is something that is relevant in React, especially Redux. And then you dive deep into the problems that callbacks is trying to solve, and then why we have thunks, what is the problem that thunk is trying to solve, all right? This independent of when this asynchronous task or task that will be resolved at some point in the future, and how now, because JavaScript is the single thread language, which is not what we think it is that it's not a language that is read one line at a time. In fact, it's made of two phases, which is the compilation phase, this compilation phase, or particularly the phase in which is going to check for the bindings as well as the scope analysis. And then you have now the execution based on that. So even though the JavaScript language is something that is run on a single thread, and because of that, doesn't have any multi-threading pattern, so concepts like concurrency and parallelism are not the same. So concurrency is the ability to now deal with tasks that overlaps at a time. All right. So pretty much like when somebody calls you and you are in the middle of a traffic, or if you are now preparing some meal for lunch and then your mom suddenly calls you, right? Or somebody calls you. Now, the idea here is that distinguish that this is now concurrency, concurrent task, and the parallelism is things that you can do at the same time. So biologically, there is a lot of things that happens at the same time. They are parallel, but cognitively speaking, we are not that. Especially when you do tasks, manual tasks, we are not true parallel. All right. So this distinguish is just to recognize that the nature of the JavaScript, especially when it's run on top of this host environment, aka the browser or the server, and now what this a thread means, to understand now the difference between the process and the threads. And the process is something that is a, despite that this name, right? A process is when a program which contains a set of instructions that are sit on disk is loaded by the OS on the memory RAM. Memory is allocated and then loaded into that, and then the processor execute those instructions. This becomes a process. So it's important to understand that this process has their own finite boundaries in memory. So one misbehaving process won't interfere in other processes. So this is known as the cron tabs isolations, or any time that you create a new tab behind the scenes, creating a new process where one misbehaving tab doesn't affect the impact of the others. So this is great, right? Because now this thread, which is a single unit of execution within a program, it is defined by the OS, and since these programs or since these threads, which example of process, particularly the program counter, the processor register, the stack trace, as well as the memory pages. So all of these processes specifically live inside of the thread, and since thread is this simple unit of execution, who defined that is the OS. So the OS via the scheduler is responsible to say what are the threads or the process that is going to be passed on and on through the to the processor, right? So this process of switching in out process with a new process and leaving and save the previous state of the process, and then now switch out so the new process can be evaluated. This is known as context switching. And because this is so expensive, because you have to now is to store this complete state of the process, which contains all of the process example that I mentioned. So all of these different states, the processor register, the program counter, the stack trace, and the memory page, and also the OS needs to keep track of the state of those applications using these internal data structures, and know when to allocate memory for those processes through the virtual memory. So because this process is quite expensive, there are now alternative like coroutines and the coroutine in what is the other one in fibers, where is the application level that needs to be handled is the concurrency to yield is the program execution and go and make it forward and backward of this flow control at the application level. So again, I mentioned this briefly because, for example, in programming languages like programming languages like PHP, Java, and Node, each one of them has their own particular ways to dealing with web server. So when you have now PHP, when this is handled by any time that a new process is created, or any time that a new incoming request is created, it creates now a new process. As you can imagine, this process is very expensive. My question is that I don't know if that's still relevant in 2025 or in which version of that. All right, but because that's go beyond the scope of today's video, it doesn't matter. The other is the Java, where you create now your server that internally, anytime that is going to listen for an incoming request, is going to create a thread for that. But as you can see now, multiple threads is going to be handled or controlled by the scheduler via the OS, which is bad for the scheduler. And another alternative is Node, that instead of uh, like other approaches, say, let me write the code to process incoming requests. In Node, you say, let me write the code to start processing the incoming request. So this is great for any input and output task that this is received, because it's gonna be now handled by the callback. All right. So in other words, it doesn't create any single thread. It doesn't create any process or thread, unlike other approaches. In fact, what it does is to any input and output operation that it receives is going to now pass through a callbacks, aka to the event handler or to the event loop, which is now defined. It's a piece of code that lives inside of a library that describe is how we're going to handle is this input and output events, and it have different phases. So Node, which use this library called as libUV, so it passed through the how do you call it? It passed through the this different phase. The initial is the timers, all right? It's gonna resolve all of the timer. The pending callback, any previous callback that wasn't handled in previous phases is gonna handle now here for any pending callbacks, all right? Each one of those phases that I mentioned is now a queue, all right? That once the entire queue is empty, is going to move on to the next one. So the timers, the pending callbacks, something known as the idle prepare for the next phase, which is the poll that say, hey, let me know for how long do I need to block to poll the input and output, and then collect all of that and add it to the poll queue. So once that is done, the next phase is the check, where it's going to check a particular callback, the set immediate, and then now the close callback. So this mechanism, all right, in which the libUV live and allow now server-side applications like Nodes to run, all right, and to handle incoming requests, it is something that is great for those languages or for a web server, but when it comes to now have to process data, for example, that come from a server or from a database or from any other service, and somehow you need to actually rely on CPU tasks, now things becomes problematic, because remember, JavaScript is gonna block the main thread. It's just one process, so that process is gonna block until it goes through the entire evaluation of that series of steps or algorithm you define. And once that is done, all right, now it's going to move to the next one, and that is send perhaps the request, so on. So this is of course not ideal, especially if you care a lot to how do you put it? If you care a lot to processing data. So for example, you are polling other services and API, right? And then you want to get that and poll that service here. Is not ideal. So that's why we have now Go, that it seems that using this mechanism now called is the Go routine, which is act like an scheduler, but at the act as a scheduler at the application level. All right. I am not that quite familiar of what's going on and how that is handled. But the point of this schedule is that instead of only having to work exclusively or instead of, so you can think of this like the node. So this go routine won't block any input and output operations or CPU intense task, which is a great stuff here. Not blocking that operation is great. Why? Well, because now you can use that CPU power, all right, as you now handle all of this input and output, or all of these incoming requests. So I think that using Go is something that a lot of uh, server might need to use instead of Python and something like that. Especially if transactions and processing power is something important for them. In the financial sector, they actually will need to do that, of course, completely. Because of that, well, it is now good to explore, but in the next video, that won't be in this video or in this series or in this course. Now, so back to what we really care, which is describing this two pillar of JavaScript. All right, we have now the X specification, the ECMAScript language, and then the asynchronous nature. All right, and now because we focus our attention on the first one, we describe briefly is what is the asynchronous nature, the callbacks, the thongs, as well as the promise, how you can work with promise, and the usefulness of promises and how you can change promise to describe now flows, data flows, okay, and why it's important to go with generators. What is the main purpose of generators that allows to stop the execution of a function, something that we can use, for example, to mimic asynchronous behavior that look like synchronous, right? So for example, the async and await. Now, and then we look at how can we handle a series of eventual values, right? Because with promise, we can only handle this one eventual value, all right? But when you need to handle this sequence of eventual values, what is the pattern that we need to do that? And this is using now observables and a library for that called the RxJS, and that's a great topic. All right. There is also another way of how you can handle this concurrency, which is the way of how, for example, Go actually is using, which is this CSP command sequence process. I think, or communication sequence process. I think it is the communication sequence process, right? Exactly, communicating sequence process. It is a member of the family of the mathematical theory of concurrency, known as process algebras or process calculi, based on the message passing via channels. Was described first by Tony Hoare in 1978 article and has since evolved substantially. CSP has been practically applied in industry as a tool for specifying and verify the concurring aspect of a variety of different systems. So this particular concept is the reason why, for example, Go is using that behind the scenes, right? So communicating sequence processor for Go developer in a nutshell, right? It's just describing this as it is. Now, but again, because this go beyond the scope of today's video, again, it's quite interesting to dive deep, but we focus our attention to this pillar, to the three pillars of JavaScript, to the ECMAScript language. So first is this system type, all right. So first we look at the exactly the type system, and this type system is involved about the primitive values, the behavior of this primitive value, the abstract operations, and then the coercion, which is part of the abstract operations, coercions and equality, right? As well as the type system that is using, or the type script. But I think this particular way of summarizing this is great. So because you are going to get familiar of what is this all about. So this primitive value, which is the undefined, null, symbol, number, symbol boolean, number string, and big int, all right, as well as object, but object is not a primitive, all right. It's another way to organize data. So we focus our attention on the primitive, right? First, on the type of operation of how you can evaluate is the value of a variable, okay? And the other is, the first is the nullish and undefined, all right? Which describing is the kind of emptiness. So what is undefined, what is undeclared, what is uninitialized, okay? And the several operators that we can use, or that we need to know that they exist, right? For empty values or the nullish values. So for example, like null and undefined, the nullish coalition, which is great for defining its default values. The other is the nullish conditional chaining. Most of the time we're not gonna use this, and if you see that, it's because somebody doesn't know about the type, or want to check that, want to make sure that the value that it's receiving here is exists. So somehow it is assuming, the author of the code, that it doesn't know the validity of this type. So in other words, it doesn't know about if this is the correct data or the correct value that we have here. So if this value is empty or not. So I prefer to, in those cases, define some traps to say, hey, let me define here this to say, I'll prefer to put now a trap here, or a gar here, as in the TypeScript they call it. I want to put now a gar, and if it doesn't pass that gar, well, let's go to now elaborate here a feedback, or provide now a feedback for them. So the other is the Boolean values, all right. Another is important, which is the distinguish, where in the distinguish you say, hey, if you're going to pass now a value here that is different from the message, but if this is null, you are going to get now that value as it is. Unfortunately, this will work. So how can we now solve this particular problem? Well, by using is, unfortunately, so how, what French toast, okay. So how can we solve that problem? One way will be is to say, well, let me now make this, all right, let me now make this, let me now is say message will be is whatever you have on the message that is different from null, all right, any nullish values, you're going to assign now to hello, all right. This is unfortunately the way of how you can truly make sure that this actually works. So if you don't believe me, I was gonna put that on test, all right, and then here we're gonna call now is greet with undefined, all right, invalid. Syntax error, but what? Syntax error where? Oh, yes, thing is this. Okay, there you got it. Oh, it's because it's this message, otherwise hello. Exactly. Oh my God! It's because I get it. It's because it's this. It's because it's because it's this. Unexpected token. Exactly. Let me do something here. Invalid syntax, but where? Which line? Oh, with hello. Okay. Invalid or unexpected token. Really? Oh, but I think it's because this is an unexpected token. Invalid or unexpected token. Oh, but I think it's I get it. No, I get it. Okay, for some reason, exactly. For some reason, it doesn't transform that into a proper token. There you get it. Now this will work. Okay. So you see that actually is evaluating that. So first it now have this compilation phase or this scope analysis phase, and then it's going to evaluate that code. So grid works as expected, right? The other is now let's say we pass null. It's gonna gracefully pass through that. What happens if we don't have this function? You may wonder, right? If we just only left this to happen. Well, the thing here is that with null, unfortunately, null will pass. So this is a way of how we can prevent ourselves for setting is null values. All right. For setting null values. This is a behavior that exists, unfortunately, you know. This is a very good interview question. This is an interview question, man. This is an interview question, bro. Interview question. Okay. Interview question. So what is the value? So what is the value of this? Exactly. What is the value of this? You may wonder, yeah, but I'm sorry, man. We are trying to filter people here. We just want us to be with people that actually know what they're doing. And here it is. All right. It's another interview question, which is, I think it is great. And then we explore now the Boolean. Nothing too fancy there. It's true or false. All right. You can flip the value using the exclamation mark. And then we look at the string. And the string in itself is a huge domain. So to make it simple, right? So we know how to create a string with this double or single quotes. However, when it comes to know what is the character encoding that is used, can you tell me what it is? If you have heard about UTF-8 or 16 and that's all that you need to know about string, let me tell you that you are far from the truth. Why is this? So how can you tell me now is what is the length of this or this or even this? All right. If you're not, no problem. Don't worry, because the idea here is to understand now what is this thing is doing. So the length of this is something that we're gonna see if when we explore about this concept of the Unicode or the character representation. All right. So because we have now for example, there is a reason why you don't put any n on domains names, because they're using now is ASCII representation, similar with the Unicode, but ASCII can represent up to 255 characters, only English characters. So now with Unicode is this umbrella terms that allows to represent numbers from 0 to 65535, and this representation, all right, or of 16-bit is a 16-bit character or binary long, and these representations allow now is to include much more icons here. This is known as the basic multilingual plan. So because anything that is beyond that, the way of how you can represent is known as the astral plane. All right, typically specifically they're using now 21 bits, but the idea here is that if you want to represent anything beyond that range that I mentioned before, we can do that by now putting this adjacent 16-bit known as the surrogate pair. Because of that, now the length of these certain emojis is the length of 2. But what happened with this? Well, glad you asked. And if you don't, no problem. It's because the representation of this is now a combination of surrogate pairs. And these surrogate pairs, if you split that, which means you split this into 60-bit and 60-bit, all right, or UTF-16 Unicode, all right, they don't mean anything. But when you combine this, it actually now represent is a number, all right? If you want to know what is the number of this, we can take a look at that, all right? I can say, hey, please give me now is the code point at this position, right? So it's gonna give you this. Which means that a surrogate pair, all right, but because it's a surrogate pair, right, is a surrogate pair, right? You may wonder, hey, what in the F is this? What in the F is 0 and 1? Well, because internally the representation of this is being used as a 3 Unicode characters. All right. Or in this case is using now this single surrogate pair. All right. So despite that we have now this, for example, if we now call this which is the code point at, all right, is this one, and the other, right? What does it mean is that the first represent is this two 16-bit together, all right, and the other represent is just one. It represents is below the surrogate parity. In other words, it can be represented is inside of this Unicode point below the astral plane. The whole point of this is that if you don't provide this, all right. So for example, if you use instead of code point, you say chart code, all right, it's gonna give you now is the astral plane value. So it's gonna give you the basic multilingual set, right? So in other words, you can use this to actually construct, all right. So for example, you can use this stream.char from chart code, all right. You can use this to actually show you the relevant icons that it belongs, or the Unicode that it needs to, right? Because this is not the same as this, you know. I know it's giving you is the last one. Look at this, it's giving you the last one. It's giving you the last one. All right? It's giving you the last one. But if you want to now say code point or chart code at 1, this is from 0, and then you want to know from 1, and then you want to actually append that to construct that with this value. I mean, it's this one. Interesting. It creates that. But if you want to say, hey, give me now the surrogate pairs, which is code point at this, you can also construct that. That's interesting. You can also construct that it actually doesn't construct that. Okay. All right. Okay. So if you say now something like this, it doesn't construct that. That's interesting. From chart code to coin point is different. It's different to chart code All right. Chart code is the code that is the code that is gonna have register in there. Is the code that we're gonna have register in there. Okay. But the other is the code point, which is where this belongs in the where this surrogate pair belongs to the list. Again, this might go beyond the scope of this, because what we really care about this is to say, well, why is sometimes we have now the length of, why is that we have, for example, now the length of those surrogate pairs, right? Or why, for example, some icons, all right, has a different length than others. And the answer is that it's because there are now is a composition of this surrogate pair, a composition of this 16-bit or this Unicode, right? That when you do that, you're going to reveal now is what those characters are made of, all right? And the same for this, for example, of the family here. Okay, for example, of the family here. Where in the family you have now all of this character set or Unicode or surrogate pair that is made of that composition. The TLDR of this is that it is important to understand that it exists the BMP, okay, that go from 0 to this 16-bit representation, 65535, all right, that allows you to represent is the basic multi-language plan, and anything that go beyond that is known as the astral plane. JavaScript interpreted this 16-bit as one single symbol, all right, or grapheme or unit. So this is the thing of understanding is how we're going to calculate this, the length computation and what's going on behind the scenes, which is part of the string behaviors, which is the next topic. So string behaviors here is first thing first, we need to understand how you can have access to. You can modify them, all right. The other is that how you can now is check how you can iterate through all of this string via is the iterator built-in object that it has, and how you can have access to that iterator via the symbol, which is another primitive that we're gonna see that, where these symbols represent is this known well behaviors. To do metaprogramming, you can think of this as hooks on certain objects, all right? I think that idea is way much more straightforward, eloquent, okay? And then when we look at the length computation, how the length is computed, and why we need, for example, to sometimes use normalizations to normalize our strings, all right? Especially if that involved is some specific characters. So this is when the internationalization comes here to play. So if you want to, for example, compare or do some length analysis or sort elements, sort characters, we can use the internationalization via the collator to say, hey, this is the alphabet that I want you to compare these different streams, all right? So we can use a collator to compare these two different words if they are the same, if they are on the same alphabet, and that is going to now tell you which comes after or another way, right? I think that's very interesting. The other is the segmenter that allow you to now is giving a particular string give you is the meaningful words. And actually I already create is a demo for that. Let me take a look at this. Of this meaningful word counter. I think this is useful to take a look at the code for it. I prefer to inspect that via page source. All right, where here we can look at what we are processing here using is the segmenter. Exactly, the segmenter. We put the segmenter here to creating as initialize. This segmenter here need internationalization, granularity word. All right, and the thing here is that, well, okay, what if I tell you this? It's gonna get that. All right, unfortunately. It's gonna get all of these different chunks of words, because, well, you can even go further to this internationalization segmenter. All right, internationalization segmenters. That's right. Here to I want to know, it's more like the options here. About the options, internationalization segmenter here. That's what it is. The options. Construction creates an intersegmenter object. Object enables local sensitive text segmentation, enabling you to meaningful items, graphemes, words, or sentence from a string. Again, it's not wise to. It's just the tag. If this is a word or a sentence, and try to do the best, right? Split the input into segments at sentence boundary and determined by local, right? So whether it's by word or by sentence, okay, we can switch that. The idea here is that we can get all of these different chunks or segments of a huge large body of text. Why this is useful? Well, because if you want to do some text analysis here, all right, when you're gonna get all of these different words, okay, you can do that. It doesn't include emojis. I just do a particularly hack to include that. You can take a look at that, but again, that's also go beyond the scope of today's video. I can tell you the hack that I use here is just to say, using a regular expression, where here I'm saying, hey, please give me is the, again, this was generated by AI. So give me is the icons that go from here and here. And you may wonder, why do we have this curly bracket here? Well, because as a way to represent that's a very good question. That's a very good question, and I know, no. Oops. That's a very good question. That's a very good question. That's a very good question. Come on, man. That's a very good question. Types and grammar. Primitive immutability. Primitive assignments. There you got it. Primary assignments. All right. Exactly. I think he described why we use this. Yeah, why we look at this? Is it, but unfortunately, graphene cluster, as explained chapter 1, throw yet another wrench in the string length computation. For example, if we take the thumb down nail here in the skin tone for medium dark skin tone, we get this. As you can see, these are two distinct code points, not a surrogate pair. These are two distinct code points that, by virtue of their ordering and adjacence, because the computers Unicode's renderings to draw the thumbs down symbols, but with a darker skin tone that is default. Yeah, but so if I go here to the string, why they call this? Escape sequence. Exactly, escape sequence. But especially for multi-character. There you got it, Unicode and string. But wouldn't work to include this character in a string since it will be parsed as Unicode escape sequence. Oh, followed by a literal 9. To address these limitations, a variation of Unicode's escape sequence was introduced to allow an arbitrary number of hexadecimals that after, because it's escaping characters. It's because the escaping characters. It's because of the escaping characters. Exactly. It's because the escaping characters. Interesting. Okay. Why this is that's a very interesting thing here. And a very nuanced as well. Exactly. String behaviors, character iterations, length computation. Alright. And when we talk about this length computation and things so on, and especially of Unicode, for example, like this, because the strings, exactly. Now I get it, bro. Okay, because escaping characters only going to count as 4 digits, right? To prevent these limitations, because Unicode can be represented from a U followed by a 4 or 6 character. So because of these limitations, we use now curly brackets to effectively say what is the variation, the number of hexadecimal here that we want to represent. This is the reason why we use this in Unicode, right? Now we do this. It's because of the parser. Interesting. It's because of the parser. And now this becomes this. So now this becomes this. That's interesting. All right. So we also look now after that, all right, about the collateral, that kind of stuff. Some demo The other is the string concatenation part of the abstract operations, that anytime that a plus operator or the addition operator is being used, is going to now give preference if one of the operand is a string or a numeric operation. And then the string comparison, which is another abstract operations, all right, that we're gonna see that better in the next coming topics. The TLDR is that we have now two equality, which is loosely equal. It follows a particular algorithm, the strict equal, and then we now have the truly way of verify is the equality in terms of type and value of the of any value here, or any type of values with using the object that is. That's interesting. That's interesting. So here, as I mentioned, well, we look at the most common string methods to go. So for example, char at, hey, I want you to give me is the character at that particular index. The at is works the same, but now for negative numbers, so you can start now from backwards, okay, which is good. The other is a char code at, and code point at, which one of them give you is the code unit, all right, whereas the other give you is the surrogate pair if they exist. Then we have now the substring, the substrings, or the slice, which is take now is a portion by providing is the star and n to get this new element here. The other is to uppercase and to lowercase, as the name suggests, right? To local uppercase or to local lowercase. The other is the concatenation, to concat several strings. Last, index of is that, hey, I want to now search for a particular value, and if that exists, give me the index. This is different from at. This is different from char at, or yeah, this is different from char at. Yeah, it is different from char at, because char at is gonna give you now is the string of that. If a valid number is outside of this range, or the empty string is missing invalid in, right? So the thing here is that with char at and at is gonna give you is an empty string if that doesn't exist, whereas with index of, all right, it's gonna give you now a minus negative or a -1 if it's not found. All right, it's gonna give you is if that value was found, it's gonna give you at which position it was found, the index. All right. The other is the last index of, which is like the index of, but in reverse. It starts from you start backwards, which is great for RTL and LLT. I think it is great, good. Includes, it's pretty much similar to search. The difference is that now includes give you a boolean if that actually match. With search returns you a number if the regular expression match. That's interesting. The other is a trim star, trim m, and trim. Okay. To actually remove any trailing string. Repeat, split, okay, to produce a new string of values, or to produce a new collection, where now it's going to split from that regular expression or that character value, all right, or that array of a string. So you're going to split this from any position or any character or string that I gave it to you. Split. This is different to a slice, and this is the difference with that substring and split. All right. So I prefer to use substring than the other. Substring to prevent any confusion. Substring and split. Then we get now pad star and pad n. Okay, which is great. Pad star and pad n, as it is. To provide now padding, and you say, hey, for how many elements do we want to add, and what will be those values? So pad star and pad n. The other is a star width and n width. Hey, is this check? So check if this star or n with this, and it returns a boolean. Similar to include and search, where now include returns a boolean, but search returns a number if that regular expression was found. All right, interesting. All right, that's interesting. Whereas the index of, it's give you the index. Exactly, it's gonna give you the index. Oh, okay. Whereas the index of is give you the index of that, if that string exists. So search for a string value arguments in the original string, optionally starting from the position specified in the second argument. So this is to, okay. So because if you do a linear search, it can be quite not effective. What you can do here is to specify from when you want to start with. Okay. Hey, I want you to start from this section or this another section, and so on and so forth, yada 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 yada. That's interesting. The index of have that capability here. All right. So most of the time is includes or search. So includes return you a volume, and a search a number. That's great. The other is match. And return an array regular expression matching result against the original string. What is the value that match return? That's a good question. Okay, it returns you now the regular expression that it found. Return you the array of that. So okay, it's gonna return you is a collection of array. Interesting. It's gonna return you a collections of array in that regard. Exactly. It's gonna return you now collections where each one of them with all of those match. For more information, see chapter 4 and the input and the length. Interesting. Now, that's very interesting. We also look at the statics helpers. So if you want, for example, if you know the chart code or from code point, you can actually have access to this hash that JavaScript actually have from all of these Unicode characters, which is great. All right. And then we can do is this. So moreover, most values, especially primitives, can be explicitly coerced to their strings equivalent by passing them to the string function. no new keyword, for example. Okay, and then you got the escape sequence for this. Exactly. So the escape sequence, a multi-character escape, as it is, where this escape sequence, okay, is, well, what are these most common escape sequence, like new line or break a lines, tab, I'm not sure what V means. The other is line continuation, multi-character escaping, whether it's with the hexadecimal for ASCII characters or for Unicode strings, all right, and also the Unicode normalization, which is something that we describe here. Unicode normalizations here. Exactly. When dealing with Unicode string that will be compared, sorted, or length analyzed, it is very important to keep the Unicode normalization in mind and use it where it's necessary. Okay? Use it where it's necessary. So if we ask Claude for this and say, hey, it is good to use, exactly, it is good to use a internationalization. Mm-hmm. Handles normalization automatically and provide local awareness sorting. Offers sensitive options for case accents and handling. Character counting can also be tricky with combining characters. Consider using graphemes aware libraries for accurate length calculations when dealing with complex scripts. This attention to Unicode normalizations prevents subtle bugs that are especially problematic in international applications. Man. Especially problematic in international applications, man. Sensitive base. Exactly. Use normalizations for that. So, in any ways, uh, in any ways, in any ways, in any ways, right? In any ways. So that's why it is important for you to. This is especially true if you. So internationalization solve a particular problem, bro. Solve that particular problem. Absolutely. Right? Absolutely. But then the function is acting as a template. Now, finally, to what we really care, which is numbers. Okay, at long last. At long last. At long last. Now, the number type contains any numeric values whose number, exactly, any numeric value, whole number or decimal, such as minus 42 or 3.14, right? Integer or decimal. Whole number, or decimal. These values are represented by the JavaScript engine as 60-bit IEEE 754 double precision binary floating points value. So then I am quite familiar to this, to this spec, all right? So the number type contains any numeric value. So the number type contains any numeric values, all right, or value, whether it is whole number, whether it is whole number or decimal, okay, and a whole number is, well, minus 42 or 3.14 and yada yada yada, right? 14, 15, which is P number. These values are represented. So these values are represented by the JavaScript, International Engineering and Electronical Engineers 754 spec. Exactly. These values are represented by JavaScript engine as 64 bits. Okay. These values are represented by JavaScript as 64 bits, bro. But at 64-bit, unlike characters that now we use is 16 bits, the Unicode, UTF-16, because there are other formats, but Unicode is the umbrella term where we can use to describe these symbols universally in a computer. So they use 16 bits, all right? This is Unicode. But now numbers use 64 bits. Holy moly. So if you do now this, right? So if we say 64 bits. If we say, well, 2 power 64, all right? 64, okay. Next thing is this, yeah. 2 power 64, okay, divide by 2. This is the number that we can now represent, okay? So this is the max value that we can represent. So this max value became something that we can have access to. It would say max safe integer, which, as you can say, is not quite close, but almost. What if I say this? I think we added too many characters there. Oh, remember, it's not 64 completely. In fact, it's less, because this 64-bit representation of number is something that because I triple equal 675 4, all right, where here they are using is now the mantissa, which is the fraction of numbers, the exponent and the fraction. So in other words, you can use, instead of this is a 32-bit floating point and the 64-bit precision here. Single precision. Oh, we talk about now is the precision. Oh, we talk about is the precision. How accurate are they to represent is those numbers? And the 64 is the same, but again here is using this. Okay, up to 52 numbers. That's interesting. So 2 power 52 numbers. Okay. Plus a sign here. But this doesn't mean, well, in any case, that's quite interesting. Two 53. Exactly. If 253 is the number, exactly, is 253 is the number that it can represent accurately. Why accurately? Because remember that at the end of the day, the values, these values are represented by JavaScript, are represented by the JavaScript as 60 bits, which means is that using the specification, IEEE 754 spec, double precision, double precision, okay, double precision binary floating points value, double precision binary point floating values. It's a double precision because they mention is one precision is 32. Okay, one precision is 32, is established as 1985, but now this standard must be updated. They mentioned is a double precision binary floating point as a way to represent way much more. And then you have now decimal 64, then you have quadruple, then you have octuple, and significant precision with 237 bits. Holy fuck. As you can see, that's insane. Oh my god. Okay. Alright. Okay. Octuple precision is rarely implemented since usage of it is extremely rare. Apple Inc. has an implementation, addition, subtraction, multiplication of octuple numbers with a 224 bits to complement significant and a 32-bit exponent. One can use general arbitrary precision arithmetic. Okay. That's interesting. Very, very interesting here. Oh my god. Double precision floating point. Double precision floating point. Exactly. Double precision floating point. Which means so JavaScript numbers are always decimal. Whole numbers, aka integers, are not stored in a different special way. An integer stored as a number value merely has nothing non-zero as it is fraction portion. Okay. 42 is thus indistinguishable in JavaScript from .20 and .2000000. Exactly. But again, JavaScript, all right? And this is interesting. This means that we can represent 2 power 53 numbers, which is a 9 followed by 15 digits. All right. Okay. Followed by the 15 digits. So far so good. We already got that. If it give you this, right? It give you this number. All right. It give you this number. So you can take a look at the representation here, which is double precision. It makes a lot of sense. And I know this might be quite duh for a lot of people. I already know that. I don't. I didn't. I definitely didn't. I didn't know that. Why? Because the way it why do it is a structure, representation, and then you get is this. Okay, cool. All right. Okay, I would like to make this fairly straightforward thing here, which is, please Claude, create this. All right, create a web app that illustrate, create an interactive website that on hover, based on this image, that on hover on each one of those cells, it tells the number it can represent in decimal. Might be silly. Might be silly, but from silly stuff we learn. Don't use, exactly, simple HTML, bro. Simple HTML. Don't use any library, React. No. Hell no. We don't need that. Just simple, good old HTML, CSS, and JavaScript. Make our life simple. Exactly. So randomized bits. So this is how now those numbers are stored in memory. All right. Mm-hmm. Mm-hmm. Okay. Double precision explorer here. Sign bit 63. Determine if the number is positive 0 or negative 1. This single bit can change the sign in any representable number. It tells the number it can represent in. That on hover on each of those cells, it tells the number it can represent. Add also the number. Randomize bits, reset to 0, set to pi, okay. To update the display, calculate the values. Oh, here we go. Oh, here we go, bro. Well, in any case, as we continue to read this, right? As we continue to read this, JavaScript numbers are always decimal. Whole numbers, aka integers, are not stored in different special ways. An integer is stored like this, right? So we can use the number as integer to determine if a number has any non-zero fractions or not. So, for example, like this. But understanding this representation is crucial for what will come in next. Okay? Because then we can ask questions like, especially if you're in a database, how is the string organized? What is the string encoding? As well as the number encoding, right? You can ask a little bit more deeper and interesting questions about it. So, we'll also look at the parsing versus coercion. All right. If a string value holds numeric looking content, you might need to convert from that string value to a number. For mathematical operation purpose, however, it is very important to distinguish between parsing conversion and coercive conversion. We can parse convert with GSS built-in parse ins or parse float. Alright? Parsing is only relevant for a string value, and it is a character by character left to right operation. It doesn't make sense to parse the content of a boolean, not a parser of the content of a number or a null. There is nothing to parse. If you pass anything other than a string value to parse int or parse float, those utilities first convert the value to a string and then try to parse it. That's almost certainly problematic, leading to bugs or wasteful parsing int. Parse int 42 is silly, and parse int 42.3 is absurd, or parse int to do the job of matfloor. Okay, parse int of 42 is silly because what it does is parsing versus coercion. So parsings pull out numeric looking characters from a string value and puts them into a number value. Exactly, it pulls up numeric looking character value, string values, and then puts them into a number, stopping once it encounters a character that is not a numeric. If parsing fails on the first character, both utilities return the special nen value, see invalid number below, indicating the operation was invalid and failed. So when parse int encounter a dot, it stop using the 1, 2, 3 in the result number. Value for parse float, by contrast, accepts this dot character and keeps right on parsing a float with any decimal digit after it. The parse-in utility specifically takes an optional but actually rather necessary second argument called radix, the numeric base to assume for interpreting the string character for the number range. So for example, if you want to now know the numeric representation of some of these characters that we used before, so for example like this, okay, and you want to know is this split, all right, and if you want to know is the values of this, you can use now the parse int. All right, I want you to parse in this value. The question is, will you? Unicode D8 3D. It tells me that this is not a number. Okay, so escaping characters is gonna count as not a number. But if I tell you that the radix here is 16, interesting. But again, anything that looks like a code. That's interesting. So escaping characters not. If radix is omitted, the behavior parsing it is rather nuanced and confusing. In that attempt to make the best guess for a radix based on what it seems in the first character. This historically has led to a lot of subtle bugs, so never rely on the default auto-guessing, always auto-guessing. Always specify an explicit radix of 10. Parse flow always parse with radix of 10. No second argument is accepted. One surprising difference between parse in and parse flow is that parsing will not fully parse scientific notations like this, instead stopping at this. It is not a valid for integers. In fact, EET stop at the E. Parse flow, on the other hand, fully handles scientific notation as expected. Interesting. Coercive conversion. Exactly. Coercive conversion. Using the operator plus in front of the value or the number as well. Other numeric representations, in addition to defining numbers using traditional base 10 numerals, 0 and 9, JavaScript supports define whole numbers, only numbers literal, in 3 other bases. Binary, base 2, octal, base 8, and hexadecimal, base 16. Okay, exactly. Other numeric representations. So, because Unicode is this umbrella term for that, I don't think it will do that. It represents a 60-bit no, but not for Unicode. Exactly. Anything that is like this, binary, octal, or hex, signify different numbers. So in other words, you want to represent is this, you can say parse int, and here you're gonna provide is the string base OX, which is D8 3D, and it can give you now is the valid number for that. That's interesting. So parse in actually going to convert that into that. That's exactly what I was looking here. So for example, if I do this and I want to split each one of them, and then say, hey, for each one of those operations, I want to get that character, okay, or let's say is the Unicode value, right? And transform that and transform the Unicode value into parse int. All right. So what I want to get now is the numeric value of that. So I'm not able to get that. Okay. So what I can do is to construct that. Always remember to pass now the radix of this stand in the parse int. And the other is whatever string you're gonna pass here, you're gonna say, hey, please let me now get the substring. Let me now get the substring from the position C1, so 0, 1, from the position 2 up to exactly. So give me is this, and I want to convert that into a hexadecimal, which is a valid number. How can I do that? Glad you asked. By doing is this hexadecimal. So OX here. And now you're gonna get that value. Substring or slice. So I want to know what is the value that we're getting here. Just the substring. From 2 to the Unicode value. Unicode value dot length. All right. So when I want you to give me that substring. Okay. It's not gonna give it to me that. But I know that I want to get is this Unicode. Alright. Or you can say replace is this. Replace this with an empty space, right? This escaping character with this. Invalid Unicode escape sequence. Oh. Escaping sequence, exactly. Escaping sequence. All right. Where you say, hey, I want you to give me this. And then I want you to find is this. And replace with an empty string. That's interesting. To replace a character how to replace a character, how to replace an escaping character character how to replace an escaping character, like for following string. Okay, globally with that, with a regular expression here. I'll be right back. I'll be right back. I'll be right back. All right. All right. And we're back. And we're back. Okay. Now, I don't know what's going on with you. Are you? Okay. It's not that hard, man. Silly. Substream. Oh, is this what I want to use here? I can say, hey, I want you to replace this okay. So I want you to replace this. But it seems that this doesn't work. Or the other is to say, hey, you know what? Give me SD substring. Let's start from this. I don't know. Substring. And why not does it work this way? That's interesting. Exactly, from all of them. So I will need to add is a new string to that and give me that? Okay. It's like adding a new escaping character to that. Alright. It's like adding a new escaping character to that. That's mind blowing, bro. That's very, very, very mind blowing. That's very, very mind blowing. Yo, come on. It's like you're hallucinating in your own way. That's another way, using code points from character that might be outside of that. Padding with 0 if needed to ensure that. For multiple character in a string. It's an actual Unicode character, so you need to use tag code to get its numeric code point. Okay, that's also silly for me. So instead of doing this, I can say is give me now the code point of this. Okay, give me now is the code point. I mean, is the code point at this. The code point at this. This is another way of how you can do this. But the idea here is to see how you can now look at a problem from different angles. Alright? And I just want is to convert those into code points. That's what it is, man. Okay, I just want to convert those in Unicode points. Alright, so once you get that, you can say now this is a number to X. I don't know where you get that. To a string. Oh, to string as a 60. Oh, okay, to get the value out of this. That's interesting. And then you can get is this string numeric exactly the numeric values from that. They are quite the same. Yep, that's right. That's what I want to. Exactly. You know? So here what we did is to decompose this Unicode and pass that in a way to get is a numeric representation of this and then transform that. So we can now is at the end of the day create the Unicode value that allows us to represent is all of this, right? So when we do this, once we can say is, well, I want to now add is, again, this might be silly, I get it, but the idea here is to see how you can now convert from one particular string with an escaping character just by getting the Unicode into a number and then convert that, you know, see things from different angles and planes and stuff like that. And then you do is this. Unicode value point at 0 to string for that. Exactly. Unicode value point at 0 to string. Alright. And for each one of them, I want to add this escaping character if I can. Yeah, I want to give now this escaping character here. Alright. Which is this. But I don't think this will work. Exactly. And you can say it's a string or substring from 1, from 0 to get that. But you can get is this Unicode. The question is that this is if you want to transform all of this Unicode into that, right? Exactly. To get all of those values there. To get all of those values there. So again, the whole idea here is to see how you can use this as transformation from strings to number. And remember that number is a 64 bit is a 64 bit through the IEEE 754 double precision binary floating points values. So numbers are stored here as integer, all right? And then we look now at the parsing and coercion. This concept of parsing and coercion, especially on numbers, is to see how you can now parse and coerce numbers. So the TLDR of this is you can now parse any number or any representation of a number, all right, as long as that string contains now a parse here. Okay, so you can parse those numbers as it is, but as long as that contain is now a string, so you can say parse int here and pass now 52 pixels, and it's going to convert. But if you have a point, it ignore anything that is go beyond that. It will going to ignore that. It's gonna take only the numeric representation. Okay, and then it stop when parsing and counting a point. Exactly. So parse int will stop until it found a non-numeric. Exactly. Parse int will stop until it encounters not a number, all right, or reach the end. And what is not a number? Anything that, of course, is not a representation of a number. So in other words, parse int might work with this. Parse int can say, hey, like this. You can also use parse int for other representations. All right. It is important to always use the radix in parse int to prevent any misbehavior. All right. To prevent any misbehavior. Why is that? Because if that exactly. We'll use radix to prevent any rather nuance and confusion, to prevent any confusing behavior. Exactly. All right, to prevent any confusing behavior. Interesting. To prevent any confusing behavior. What is the other one? Parse in, false. And the other is parse floats, always parse with a radix of 10. So no second argument is accepted. Parse floats always parse into a radix 10. It allow scientific notation. And well, floating numbers, unlike parse int. And now the coercion, because one of them is the parsing and the other is coercion. Coercion can be achieved do number or plus operator. For example, like this. Now, then we look at the other numeric representations, whether it is binary, hexadecimal. Most of us, unless you're working with low-level things, you might see this or not. All right. It is important to realize that you are not defining a different number, you're using a different form to produce that. Similar to this. To string in a binary, that's interesting. By default, JavaScript represents the underlying numeric value input string fashion with standard base 10 form. However, numbered values have built-in to string method to produce a string representation in any specific base radix, as with parser in the range of 2 to 36. That's interesting. This is other numeric representations. So other numeric representation. And how can we now use it like this? All right. Now, you can round trip any arbitrary radix string representation back into a number using parse int with the appropriate radix. My h42, which is this, you can parse that to string 23, and it's gonna give you is parse this and this to base 23. You can round trip any arbitrary radix string representation back into a number using parse int. Another allowed form of a specific number literal is using scientific notations. So 4.2E1 or 4.2E1 means is that 4.2 powers 10 to 1. Exactly. Powers 10 to 1. This exponent can optionally have a sign or not. So you can either use with a sign or not to represent these notations. By default, JavaScript will represent e.g. string values, etc., either very large or very small numbers, specifically if the value requires more than 21 digits of precision. Number with smaller absolute value closer to 0 than these three holes can still force into scientific notations, form as a string. The optional argument to exponentially specify the number of decimal digits to include in the string representation. Another readable affordance for specifying numeric literal in code is the ability to insert as a digit separator whenever it is convenient, meaningful to do so. For example, this some big power of 10, total cost in pennies. The decision to use 1, 2, 3, 4, 5 no separation and 1, 2 floor 3, 4, 5 like or 1, 2, 3 is entirely up to the author of the code. JavaScript ignores separators, but depending on the content, 1, 2, 3 could not be semantically meaningful, readability-wise, than more traditional 3 digits groups from the right separation. So another readability affordance for specific numbers literal is in the code is the ability to insert a floor as a digit separation wherever it is convenient, meaningful to do so. That's interesting. That's interesting. That's interesting. That's interesting. So you can represent this number like this. Okay, so big number where you say, hey, this is from readability perspective. Oh, that's interesting. That's interesting. That's interesting. We can also use notations for this. All right. We can use scientific notations. So scientific notation, and we do this well because these numbers are pretty big, bro. And we're doing it with the scientific because we are pushing the boundaries. That's what happened. We are here pushing the boundaries. We are here pushing the boundaries of what is capable and what is not. You know? And what is capable and what is not. So, well, and what is capable and what is not. And the other is the representations from a perspective wise, or from a readable wise, man. And from readability. We can represent this. That to me is interesting, man. Absolutely. Well, actually, the bitwise binary representation, it is a technical standard for binary representation of decimal number. It is widely used by most common programming language, JavaScript, Python, Ruby, etc. I'm not going to cover it exhaustively, but I think it is a brief primer of how numbers work in language like JavaScript. It's more than a warning, given how few programmers have any familiarity with it, including myself. In 64 bits, IEEE 754, so-called double precision, because originally IEEE used 32 bits, and now it is double that. The 64 bits are divided into 3 sections. 52 bits for the number base value, aka fraction, and these are significant, exactly. And 11 bit for exponential and to rise to before multiplying a 1 bit for sign of the ultimate value. So since only 52 of the 64s are actually used to represent the value, represent the base value number, doesn't actually have 264 values in it. According to the specification for the number type, the number of value is precisely the number of value is precisely 264 minus 253 plus 3, or about 18 quintillion. So 264 minus 2 Jesus 253 plus 3. So this is or about quintillion, split about evenly. So you have that number, And when you divide this, you have now this representation, which is, if you take a look now, the number max safe integer, you got is something that is less than that. Alright, so these bits are arranged left to right, and so is this. So the sign, the bit, the exponent, and the mantissa. So the number 42 or 420000 will represent by these 3 bits, right? Exactly. So you got the exponent, the sign, and the mantissa, right? How do you represent that? The sign bit is the sign bit 0 meaning the number is positive, 1 means negative, and I don't think that you actually create what I want to. So if I ask a new chat here and I run this, the sign bit is 0 meaning the number is positive, 1 means negative. The 11-bit exponent is binary, exactly, which base is 10, but in IEEE this value is represent this value is interpreted as being stored on site with an exponent bias of this, meaning that we're shifting of exponential range from this to this, or from 1 to 2046, where 0 and 240 and 2047 are reserved for special representation. So take 1028 and subtract the bias 1023, which gives an effective exponent of 5. We raise 2 to the value of 2 power 5, giving 32. If the subtracting 1023 from the exponent value give a negative, aj minus 3, that is still interpreted as 2 exponents. Raising 2 to the negative numbers, just producing smaller and smaller values. The remaining 52 give us the base value, interpreted as binary decimal, with all trailing zeros. Converting that to base 10, we get 1.3125. So this is interpreted as binary decimal. Finally, then that multiplied by 32, already computed from the exponent, the result is 42. Holy moly, bro. But this is the mantissa. All right. This is the mantissa. This is the mantissa. Interactive binary number system. And the other is this. exponent bias. Mm-hmm. Mm-hmm. Number limits. As might be evident, now that you have seen how IEEE 754 works, the 52 of numbers base must be shared, representing both the whole number portion, if any, as well as the decimal portion of the intent number value. Essentially, the larger the number, the larger the whole number to be represented, the less bits are available for the decimal portion, and vice versa. This is something important from all of this, right? Because we talk about is the is this okay? It's because of this, all right? The number limits, all right? That is using now 52 for Mantissa. It used 52-bit for Mantissa, 8 for exponential, and 1 for a sign. So why this is important? because the larger the number, all right, so essentially the larger the whole number portion to be represented, the less bits are available for decimal points, and vice versa. That's the number limitation from. So if we take a look now, is the number value max safe integer, or max value is this, but you might expect that value to be decimal value given the representation, but on a closer inspection is approximately 2 power 1024 minus 1. That seems much more like it should be an integer, right? We can verify number that is integer, number that max value. But this is the decimal representation. Which is a minus negative, a positive value. Mm-hmm. Mm-hmm. That's interesting. So the idea of this, all right, the idea of these two, the idea of these two, right, is that we can now take a look and be now more. We have a more interactive stuff of what's going on there. So we can get a more precision of what is doing behind the scenes. So anytime that we store a number, it's going to use these internal representations using the double precision floating points, convert that, reserve that space in memory for this, and now save that and keep that state as long as we have now power on our computer. Holy fuck. As long as we have now powered on our computer, so that charge will keep in memory. So you will have now that. Holy moly. It is mind blowing, bro. It is definitely mind blowing stuff, bro. Absolutely, bro. It's like absolutely, bro. Absolutely. Absolutely, bro. Absolutely. Absolutely, bro. Mm-hmm. So given, okay. So given the following with a number, exactly, declare a variable with a number, how this variable, declare a variable with a number, how this variable is being, how this number, declare a variable with a number, let's say 2025, how this number is converted into a IEEE 64 2 precision, twice precision, binary decimal, twice precision. Twice precision. Exactly, twice precision. Twice precision. Oh, double precision binary point. Exactly. Double precision, double precision, binary point floating, okay? Declare a variable with a number, declare a variable called year with a number 25. How this number is converted into EA3, how the OS, how the browser talk to the OS to reserve space in memory to allocate this variable, and how this number and how this number persists, since they are now, and how this number persists in the RAM thanks to the and how this number persists in the RAM and how this number persists in the RAM thanks to the transistor, no, because memory is memory. Okay. So is memory RAM made of capacitor, right? Capacitor, right? Circuit transistor, typically. Okay. And how this number persists in the RAM, but instead of using now, you use a circuit of transistor to switch and down. They can maintain this thing as long as power is supplied. The capacitor holds the electricity charge that represents 1 or 0. Since capacitor naturally leak over time, the RAM needs to be refreshed consistently, hence dynamic. And that's RAM. Most of the main system RAM in computers today is DRAM. So when people say RAM, they usually refers to this static RAM. I don't sure if that's RAM. Okay. Thanks to the capacitor. Thanks to the capacitor, how these numbers and generate image, a timeline that describe with image when in JavaScript or transistors. How this number persists in RAM thanks to capacitor or transistors. There is a lot of layer of abstraction, bro. There is a lot of layer of abstractions, bro. Absolutely. There is a lot of layer of abstractions, man. Absolutely, man. Holy moly. I don't know what you are creating, but well. And pass to the VA engine. The IEEE 72 precision is in the store. Before you have a huge sign exploding and dependencies, and of course that goes beyond. And then the browser and operating system memory requests. The browser JavaScript engine requests memory from the OS, which say this is a simplified memory allocation flow. V8 Heap Manager requests a bit browser process called the OS. Allocate that OS kernel allocate virtual memory page, and then the MMU maps virtual physical address, and this physical address is reserved. So browser operating system talk to the MMU to the physical RAM, and then you get is this physical persisting in RAM capacitors. It's stored in DRAM capacitor. Each bit corresponds to a charge of this. So 8 bytes representing 60 bits. Okay. So one DRAM capacitor is a bit or a zero, which is char, or this char. It is refreshed roughly at 1,000 times per second. Physical nodes. Each bit is stored as the presence of 1 and 0. So JavaScript number journey from code to silicon. Holy Mosaic is going to talk. So is a browser that is going to talk to the OS, and the OS is going to allocate that memory for us. It's going to allocate the memory in the physical RAM for us. That is mind blowing. That is mind blowing, bro. Absolutely. That is mind blowing. Mind blowing. Yep. And then you got now the number limits. Holy moly, bro. Okay. But it's going to talk to that. In safe integers number, as well as double zeros, an invalid number. So we have looked so far that the number limits, as well as the safe integer limits, the double zeros, and the invalid numbers. And you don't know GS. String behavior, and then the number behaviors, bro. Floating point imprecision, which is something that we know. Pretty much all programmers need to be aware of this and make sure they're careful about this kind of gotchas. It is somewhat amazing in a disappointing way how few of them have any idea how IEEE 750 work works. If you have taken your time reading this, understanding this concept so far, you are now in the rare tiny percent who actually put in the effort to understand the numbers in the programs. Epsilon threshold. And numeric comparison. Exactly, the behaviors and the numeric comparison. Is never equal to itself because it has its own values, a numeric relationship comparison. Exactly. Mathematical operations. With this, string comparison, anytime that there is a string, it will favor that. It will do a string concatenation for additions only, and for other is going to coerce that into a number. D2, these two, both operands are coerced to numbers. And in two numbers. That's interesting. This is part of the behavior of each one of those. Increment and decrement. Bitwise operation. I think that may go beyond that, but it's important for you to know that. Number value methods, to exponential, to fix, to precision, to fix, and to local string. Okay. Static number properties. Number epsilon, number n, number mean safe integers, number mean value, negative infinite, static number property, static number helpers. Okay, helpers, numbers, and static math namespace. Big ins and number don't mix. Exactly, big int and numbers don't mix. And primitive are the foundationals, bro. Holy fuck. Oh shit. And then we look at the object values here, which is the behavior and all of that kind of stuff. Other building objects like this, and proposal, the tuple, and that kind of stuff. Coercion versus explicit versus implicit. Implicit, bad or, as well as the abstract. And here it comes through the coercion value of the abstract operations. Exactly, abstract. To primitives, to strings, to number, equality comparison. All right. Equality comparison, high abstracted equalities is strictly equal, is loosely equal, where it's going to pass through a specific algorithm for that. Then you look at the relational comparison, is less than is abstract. String comparison is less than A and B, is less than 101, 12, is less than chicken. Concrete coercion to Boolean. Oh, the to Boolean, exactly. The to string. The to number. And what is doing the to number? And what are some of the edge cases? Mathematical operation, piecewise property access. To primitive, Oh, it's explaining is what's going on down deep into this. Object to Boolean, unboxing wrapper a primitive, overriding default to string, overriding to primitive because this is symbols that you can have access to that. Okay, fellas. Hmm. Okay, fellas. Okay. Hmm. Hmm. I think this particular code is very important, at least to upload that. And I will do that. And I will do that. And I will definitely do that. A demo. Hmm. I think this is quite interesting, though. Definitely. Very, very interesting. Very, very, very interesting. Yep. Very, very interesting. Hmm. Hmm. So that's interesting. And that'll be all for this video. Take care. Bye bye.